Hello everyone and welcome back to lecture 6. In lecture 6 we talked about insulation, so let's look at how we can calculate the thermal insulation resistance for any particular geometry. Okay, so let's say we have a system here that we have a pipe where a fluid is flowing at high temperature, that is steam, at a high temperature of 320 degrees centigrade, and then you have insulation around it, and then at the top of this pipe you have, let's say, it's exposed to atmosphere or air, so there is some form of convection as well. Okay, so you are given several set of data here. So you are given, for example, if we simplify it, you are given uh, the diameters of different pipes. Okay, so if you look at this geometry here, so you have the inner surface, this one is where the hot fluid is moving, so you know the diameter of that, the inner diameter of the pipe. And then you have the pipe wall, so that is the pipe wall, and then you have the outer surface of the pipe. Okay, and then outside that pipe you have the insulation itself, and then you have the third um, uh, area, or third, sorry, diameter of the pipe, and then after that you have the that is this pipe is exposed to the air. Okay, in addition to that, you are also given different other geometry, heat transfer related data. So you know H1, that is the heat transfer coefficient of the convection inside. You know the conductivities of the iron pipe and of the insulation, and you know the combined heat transfer of radiation and convection for outside the pipe. Okay, so that is exactly what we did in the lecture. Okay, you are also given what is the temperature inside of the fluid. You are given the temperature of the outside fluid, that is the air, for example, but you are not given the intermediate temperatures, the temperature at the inner side of the pipe, the temperature at the outside of the pipe, and the temperature at the surface of the insulation, that is T3. Okay, so before we go into solving this problem, we need to make some assumptions. And the first assumption is that we assume that it is a steady state process. Okay, it means that the things are not changing in time. We are also looking at one-dimensional problem. It means that we are looking that the heat is being transferred only in one direction, that is in the direction of radii. Okay, and we have constant thermal conductivities. They are not changing with time, or they are not changing with temperature. Okay, so if we use all this information, we can see that we have convection that is happening inside the pipe. Then we have the conduction that is happening out in the wall of the pipe itself. Then second, conduction in the insulation layer, and then we have the final convection that is happening outside the wall of the pipe. Okay, so if you use the analysis that we did in lecture 6 and also in the problem sheet of lecture 5, so you can see that we have the convection resistance, then we have the conduction resistance, second conduction resistance, and finally we have the convection resistance. So we have four resistances in series. Okay, and these are the inside temperatures and outside temperatures. We don't know anything about the intermediate temperatures. So the first step that we need to do is to calculate the surface areas of this system. And if you go back to the question, in part 1, you are asked to calculate the heat loss from steam per unit length of the pipe. Okay, so we need to calculate Q per unit L. Okay, or another way of looking at it is that we can assume that the length of the pipe is 1 meter, and then we just need to calculate Q. In part 2, we need to calculate what are the temperature difference, for example, between the inner fluid and the outer side of the pipe, and between the outer side of the pipe and the outer side of the insulation. Okay, so let's look at part 1. So to calculate the heat loss, we need to first calculate the surface areas, because we need to know what is the surface area of the pipe that actually is losing heat. So for the inside of the pipe, we can calculate 2 pi r L, so that is the surface area of the pipe, okay, and we know 2 pi, that is 3.14 times the diameter of the pipe, because it was 5 centimeter, so we make it half and then we convert it into meter, so it's 0.025 meter, and we are assuming that we have a length of 1 meter, okay. So by using this formulation, we can calculate the inner surface area of the pipe, and we can do the same analysis for the outer surface area of the pipe, and we have the second value, okay. So the other thing that we need to know is what is the resistance, okay, and normally we use this kind of method when the geometry is complex and we want to keep our analysis simple, because we know that Q is equal to delta T over R, okay, and this R can be calculated in a very simple way, just looking at the heat transfer coefficient multiplied by the surface area for convection, for example, and we can calculate what is Q based on the temperature difference, okay. So if you look at the individual resistances based on the mechanism that is involved in that resistance, so we know that the inside of the fluid we have convection, so we use 1 over HA1. We know the areas already, we know the values of H from the question, so we can calculate the inner resistance. Similarly, we can calculate the resistance due to conduction. We know this formulation from lecture 2, and also we discussed in lecture 5 and lecture 6. So we can write it just by adding the value, putting the values of R's and L and K's. We can calculate the resistance of conduction of the pipe. Then we can calculate the resistance of insulation using the same formulation, just changing the values of R's, because when you are going from pipe to the insulation, the area, the radii are changing, okay. And then we have the final resistance from convection, again looking at the heat transfer coefficient and the surface area of the overall radii of the system, okay. So once we know all the individual resistances, we can sum it up to get the total resistance, because the resistance, all these resistances are in series, so we can sum them up just like that, and we have the overall resistance of 2.61 kilowatt. We know what is the delta T from the inside of the fluid to the outside. So here we have 350, and at the outside we have 5 degrees centigrade, and we need to convert these, for example, temperatures is in Kelvin, because we are using heat in Kelvin. So our total is the given value here, and delta T is 305 Kelvin. So if you take the ratio of these two, we know that the heat loss per unit length of the pipe was 121 watt, okay, because we assume that the pipe was 1 meter long. Now for the second part, we need to calculate what are the intermediate temperatures, and the easiest way to do is to look again at the same formulation here, that is Q times delta T over R. Q is equal to delta T over R, and we can rearrange it in the form of delta T is equal to Q times R, that is the resistance of the geometry, okay. So if we want to calculate the temperature difference across the pipe, it means from the inside of the pipe to the outside of the pipe, we have the Q. We know what is the resistance of the pipe that we calculated here, that is given here, for example, R1, and we can multiply these two and we can get the temperature difference, okay. Similarly, for the case of insulation, again we use the same formulation, but now the resistance of the geometry is not because of the pipe, because we are across insulation, so we are looking at the R of insulation, and if you use the value from the same previous calculation, you can get delta R of the pipe, okay. So what is important here to notice is that when you are looking at delta T across the pipe, there is hardly any temperature difference or temperature drop, for example. And when you are looking across the insulation, you can see there is a huge temperature drop, and what it is showing you that the insulation is working and is trying to conserve heat inside the system, because the temperature drop of the pipe itself is really low. Okay, and so that is why we can calculate. Now we know the different inside and outside temperatures. We know T infinity, so from delta T we can calculate what is T2, and similarly we know T1 infinity, and from delta T we can calculate what is T1. Okay, so that is the solution to this problem. Thank you for your time.